Okay, so this was about the Boltzmann transport equation, and we reached up to here. This was the Boltzmann transport equation. Df by dt is equal to partial differentiation of f with respect to t plus v dot gradient of f plus fe dot gradient of pf, which is equal to 0. But I told you here we have not considered the scattering effects, right? Because the electrons are colliding with the positive ions, as well as the electrons are also colliding with themselves, right? But the electron-electron interaction we have not considered while deriving this equation. So that impact needs to be considered, because this will hugely change the Boltzmann transport equation, right? So let us consider that part also. Let us assume that at the position f, x, p, t, the scattering of the electrons takes place, and you know that it may be in scattering process, it may be out scattering process, right? The electron may come to the vicinity of f and they may collide with the other electrons, or the situation may be an electron is colliding, two electrons are colliding within the vicinity of this f, and the one of the electron is going outside, right? So that is a scattering, that is out scattering process. So there may be in scattering, there may be out scattering processes, right? So the rate of change of f, because f will change. What is f? F is the probability of finding the electron within the vicinity of x, p, t, right? So if f is the probability, then rate of change of f with respect to t due to the collision, or due to the scattering of due to scattering, you can say, due to the scattering of electron and electrons, this is equal to a constant c multiplied by f, and this is further equal to the in scattering, the electrons coming inside due to the in scattering process, or the electrons going out due to the out scattering process, okay, divided by the mean free path. Okay, so it means that see here, this could be further explored as, this is further equal to minus f t r. We are not taking it as x because we are talking in 3 dimension, right? So now x is replaced by r. So this is f t r minus f naught t r divided by tau m. Okay, so here this term, this first term, or you can say this second term, this is the probability of finding the electrons at equilibrium, and the second term fpr, this is the outscattering electrons, outscattering electrons. So if we denote this difference, this numerator, by equal to delta f t r, then the rate of change of f with respect to t, or you can say c f, is given by minus delta fp r divided by tau. I have used this relaxation time as tau, so m is not required over here. Don't write it as m. This is simply tau. Okay, so this is delta f by tau, relaxation time. Okay, which is equal to the rate of change of f, you can say df with respect to dt. Yeah, df with this divided by dt. Okay, so if you differentiate this equation on both sides, then the result that you are going to obtain is f minus f naught, which is delta f, is equal to f minus f naught. Since we have done similar type of integration in the last article, so I'm not going to do it in detail. So this will give you the result f minus f naught is equal to f minus f naught exponential minus t upon tau. Okay, so this is the modified Boltzmann transport equation when you are considering the scattering of electrons. Okay, so what does this equation means? This is actual Boltzmann transport equation in presence of scattering, process. Okay, so therefore when an external field is removed, you can see from this equation, when the external field is removed, f minus f naught, it decays to 0 in this fashion. Okay, right? So this is the resultant Boltzmann transport equation, and this is very much helpful to determine the transport properties of the metals. Okay, so this was the Boltzmann transport equation. Now we are going to switch for the next article of the syllabus, which is thermal conductivity of metals. Thermal conductivity of the metals. Okay, so you know that heat conduction is the transfer of thermal energy from a hot body to a cold body when both of the bodies are brought into contact, right? When there are two bodies and when they are brought into contact, and suppose the one body is kept at hot end and let's say this is the cold one. So when these two bodies are brought into contact, there is a transfer of heat energy from hot body to cold body. You know that, right? Okay, so why this happens and what is the mechanism behind this? How the transport of heat energy from hot body to cold body takes place, right? What is something which is carrying that energy? Okay, are they electrons, are they phonons? How the transfer of energy takes place from one electron to another electron, or from one atom to another atom, right? And how the transfer of heat energy takes place from one end to another end, right? So this is something which we are going to study in this article. Okay, so let's say we have a bar of material of length x whose ends are placed at different temperatures. Let's say we have a bar. Please mute your microphone, students. Okay, so we have a bar of length, let's say x. Okay, so let's say this is the hot end and this is the cold end. Okay, so the transfer of heat energy takes place in the reverse direction of the gradient, right? See, the temperature is changing from atom to atom, from electron to electron, the temperature is changing, right? And the change in the temperature with respect to the distance or with respect to the length of this bar is known as the gradient, right? This is gradient dt by dx, right? So if we define the gradient by this, then the amount of thermal energy Q which crosses unit area of this bar per unit time is proportional to temperature. Okay, this is proportional to the temperature gradient dt by dx, right? So the proportionality constant here, if we say that Jx is the amount of heat energy which is being transferred from hot end to the cold end, then JQ must be equal to minus sigma T dt by dx. Okay? Heat of energy is directly proportional to the rate of change of the temperature with respect to x, right? If here the temperature is 20 degree, here the temperature is 30 degree, so the gradient will be the difference of the temperature divided by the difference of the length here and the length here, right? So the heat transfer is proportional to the gradient of the temperature with respect to x, right? That proportionality constant is removed by this thermal conductivity by this sigma T, and sigma T is known as the thermal conductivity of the materials. Okay, so sigma T is called thermal conductivity. This is called thermal conductivity. Okay, here what is the significance of the negative sign? So negative sign here indicates that the heat flows from hot end to cold end, right? Which means that the heat flow is opposite to the gradient. This is opposite to the gradient dt by dx, right? Okay, so the unit of, yeah, this is very important. The unit of thermal conductivity sigma T is watt per meter per Kelvin. One important thing that you should note that thermal conductivity decreases slightly with increasing temperature. Okay, for example, sigma T for copper, if I say, if you raise the temperature up to 1000 degree centigrade, then in this range the conductivity of copper decreases by 20%. Okay, similarly for iron, sigma T for iron decreases by 10%. Okay, so we can say that thermal conductivity decreases slightly with increasing temperature. Okay, so this is another important feature. In insulators, the heat is carried entirely by the phonons. You might have heard about the photons, phonons, right? So in insulators, the sigma T is due to phonons. However, in metals, the situation is different. In metals, heat may be transported by both electrons as well as phonons. In metals, heat may be transported both by phonons as well as by electrons. Okay, so therefore the contribution in thermal conductivity of metals is due to the both of the things, the phonons as well as the photons. So the total thermal conductivity of metals is due to the thermal conductivity of the electrons plus the thermal conductivity of the phonons. However, it has been observed that, yes,
मैम प्रीवियस सीट खाना एक बार.
okay, is it okay?
Yes ma'am, done.
Okay, great. I told you that the total thermal conductivity of the metals is due to the impact of the both. The electronic conductivity means the thermal conductivity due to the electrons plus the thermal conductivity due to the phonons, right? However, it has been observed that the thermal conductivity of the metals due to phonons is very less, and this is approximately equal to 10 raised to power minus 2 times the conductivity due to electrons, right? So this is having a very less value as compared, means the conductivity, the contribution of the conductivity due to electrons is quite high as compared to the contribution due to the phonons, right? So most of the times we ignore the contribution due to the contribution in conductivity due to phonons. Okay, so most of the time it is being neglected, right? So in order to now let us see, the aim is to find an expression for conductivity. We need to find a mathematical expression for conductivity. हमने last article में we find the conductivity for we find the expression for the electrical conductivity. Now we are going to find out the expression for the thermal conductivity. Okay, so in order to find the expression for thermal conductivity, consider a copper conductor in the form of a rod of uniform cross section area, maybe 1 square meter. Let us assume that a thermal gradient we established in this rod, okay, means, see, let us suppose that we have a rod of copper whose area is, let us say, 1 square meter, okay, and thermal gradient is established in this rod. That means that we are supplying heat from this end, from one end, such that there is a temperature difference at one end and the another end, right? So this means that we have established a temperature gradient. Okay, so after this, let us consider three layers: layer A, layer B, and layer C. Let's say this is A, this is B, this is C. So consider three layers A, B, and C normal to the direction of heat flow. Normal to the direction of heat flow. Okay. Let each of them is separated by a distance lambda. So the distance between A and B is lambda, and the distance between B and C is also lambda. Okay. So the where lambda is the mean free path. Where lambda is the mean free path. Lambda is the mean free path of the electron gas in the metal. Okay. Next thing, let us assume that, see, the temperature here at this end will be different, and the temperature here at A will be different, the temperature here at B will be different, and the temperature here at C will be different, right? Now, how much temperature is changing? How much temperature is changing, right? What is the rate of change of the temperature with respect to X? Okay, so let us assume that if T is the temperature here at point B, then at the point A, the temperature will be T plus dt by dx, which is the rate of increase of the temperature with respect to x multiplied by lambda, because here the distance is lambda. So agar lambda distance hai, so for lambda distance this temperature change must be this dt by dx multiplied by lambda, right? Similarly, let us say that the temperature here at the point C is T minus dt by dx lambda, right? Why we are doing it like this only? Because see, A is the hot end and C is the cold end, right? So here the temperature is less, here the temperature will be maximum, right? So this is plus, this is T minus this quantity. Okay. Similarly, because this energy, the thermal energy, is directly proportional to temperature. So that energy, if the value of energy at point B is E, then the energy at the point A will be E plus dE upon dx multiplied by lambda, and the energy at point C will be E minus dE by dx multiplied by lambda. Okay, so this is the situation. Now we know from the kinetic theory of gases that the number of electrons flowing in a given direction through unit area for unit time is what? आपने free electron theory of gases पढ़ा हुआ है, right? Let us say if this is any volume and it encloses n number of total electrons, then how many electrons will be there in one particular direction? Let us say if c bar is the average velocity of those electrons, right? We have three perpendicular directions. Okay, so movement कौन कौन सी डायरेक्शन में होगा? x में भी होगा, y में भी होगा, z में भी होगा, पॉजिटिव x में भी होगा, नेगेटिव x में भी मूवमेंट होगा, नेगेटिव y में भी मूवमेंट होगा, नेगेटिव z में भी मूवमेंट होगा. So tell me, if n is the total number of electrons within this volume and c bar is the mean velocity or average velocity of these electrons, then how many electrons will be there in one single direction? There are 6 directions at all. So how many electrons will be there in one single direction? You have studied it in kinetic theory of gases. Yes.
Six.
Yes.
6n.
6 n.
Yes.
Is that 6n? Yes. Anyone else? I told you total number of electrons are n, right? So number of electrons in one single direction, it has to be less than n, na? 6n कैसे हुआ? And we are talking about the number of electrons per unit area per unit time, right? Per unit area per unit time. So C has also C has to be considered. C bar has to be considered. Yes. Anyone else?
Ma'am, will you please repeat?
Yes, my question is, if there are, if we have this volume, let's say V, okay, and N is the total number of electrons in this volume, and these electrons are moving with a mean velocity c bar, right? Then how many electrons will be there in one single direction? See, there are three perpendicular directions, right? And the negative of these directions has also to be considered. So there are, in total, there are 6 directions, right? So if we want to take the total number of electrons in one single direction, then how many electrons will be there for that? This is very simple. बेटा 12 एप्पल्स को अगर 6 में डिवाइड करना होगा तो क्या करोगे?
Ma'am, twice of it.
तो हर
Like-
डायरेक्शन में कितने आएंगे बताओ? अगर n टोटल नंबर ऑफ इलेक्ट्रॉन्स हैं तो 6 डायरेक्शंस में कैसे डिवाइड करोगे उनको?
That will be
1 by 3 and 6.
3 नहीं है ना बेटा, 6 डायरेक्शंस हैं.
Oh, sorry,
6.
by 6.
So
1
this
by
will be 1 by 6 n. Now we are talking about unit area per unit time. Per unit area per unit time. तो velocity से भी multiply करना पड़ेगा, right?
Yes.
Yes.
Yes, ma'am.
Okay, so now you got it. Okay, so this means that 1 by 6 n c bar is the total number of electrons in one particular direction. Okay, moving in one particular direction. Okay, so therefore the excess of energy transported by the process of conduction through unit area in unit time कितना होगा? एनर्जी ट्रांसफर कितना होगा? एनर्जी ट्रांसफर विल बी इक्वल टू सिंपली व्हाट? द नंबर ऑफ टोटल नंबर ऑफ इलेक्ट्रॉन्स इन वन डायरेक्शन मल्टीप्लाइड बाय rate of change of
dt by x.
yes, rate of change of this yes lambda, क्योंकि हम सिर्फ यहाँ पे a b और c की बात कर रहे हैं, ठीक है? तो इसलिए हमने c, यहाँ पे आपका एनर्जी E था, यहाँ पे आपका एनर्जी कितना हो बढ़ गया, dE by dx इंटू लैम्डा हो गया, राइट? और यहाँ पे आपका एनर्जी कितना हो गया, dE by dx लैम्डा हो गया. ओके, सो yeah, you're right, this should be x. Okay, so it means that डिफरेंस कितना है, एनर्जी में कितना डिफरेंस है, dE by dx का डिफरेंस है, राइट? सो यहाँ पे अगर हम B की बात कर रहे हैं, सपोज वी आर टॉकिंग अबाउट द पॉइंट B, राइट? देन हाउ मच एनर्जी इज बीइंग रिसीव्ड बाय B फ्रॉम द पॉइंट A, और हाउ मेनी एनर्जी इज बीइंग ट्रांसपोर्टेड बाय B टू A, right? See, there are two different situation, energy difference between A and B and energy difference between B and C, right? तो अगर B की बात करें, B मिड में है, ओके, सो B से C की तरफ एनर्जी जा रही है, सिमिलरली A से B की तरफ एनर्जी जा रही है, सो B जो है वो E से एनर्जी रिसीव कर रहा है, कितना, dE by dx, और कितना C को कितना ट्रांसपोर्ट कर रहा है, dE माइनस dE by dx, राइट? तो B जो है वो मिड पॉइंट है, B एनर्जी रिसीव भी कर रहा है और ट्रांसपोर्ट भी कर रहा है, सो नेट एनर्जी चेंज कितना होगा वो हमें देखना है, B पॉइंट पे हाउ मच एनर्जी विल बी चेंज्ड, that we have to observe. Okay, so it means that energy received by B, this is the energy received by B from A, and lambda is also there, ठीक है? ये है ना आपका एनर्जी चेंज, dE by dx into lambda, dE by dx into lambda. So total energy received or total energy received by B in one particular direction is equal to 1 by 6 n c bar dE by dx into lambda. Okay, which is equal to, इसको हम सिंप्लीफाई कर सकते हैं, n c bar lambda dE by dx. Okay, similarly this is the energy received by B from A. Okay, similarly the energy transported by B to C, energy transported by B to C is equal to how much, negative of 1 by 6 n c bar lambda and dE by dx, total energy transported. Okay, so this is the energy transported by B to C, and similarly the energy received by B from A is this one, 1 by 6 n c bar lambda dE. एक नेगेटिव होगा, एक पॉजिटिव होगा, क्योंकि नेगेटिव क्यों होगा, क्योंकि माइनस हो रहा है एनर्जी में, पॉजिटिव क्यों होगा, क्योंकि एनर्जी रिसीव हो रही है. ओके, सो नाउ net heat energy change, net heat energy change through B in unit area per unit time is 1 by 6 n c bar lambda. कितना होगा, नेट आपको देखना है, डिफरेंस कितना हुआ, तो जो रिसीव हो रही है माइनस जो ट्रांसपोर्ट हो रही है, राइट? सो दैट माइनस this transported energy, so 1 by 6 n c lambda dE by dx माइनस ट्रांसपोर्ट कितनी हुई, माइनस 1 by 6 ऑफ n c bar lambda dE by dx. ठीक है, नेट एनर्जी चेंज इतना हुआ. ओके, विच इज इक्वल टू, इसको आप सिंप्लीफाई करोगे, सो दिस इज इक्वल टू n c lambda divided by 3,
3d by dx.
yes, dE by dx. So this is the net energy change at the point B. And this net energy change must be equal to the product of the thermal conductivity and temperature gradient. क्योंकि आपने सबसे पहले यही बोला था, ये क्या था आपका, ये आपका नेट एनर्जी चेंज है, मीन्स जे क्यू है आपका नेट हीट एनर्जी चेंज कितना हो रहा है, एंड दिस इज इक्वल टू व्हाट, जो आपने सबसे पहले बोला था, दिस वन. इफ दिस इज इक्वेशन
Heat
नंबर
transfer.
1, yes, heat transfer. So this is minus sigma T dt by dx. Okay. So इसको अगर मैं equate कर दूँ, so let's say this is equation number 1. So equating equation 1 and equation number 2, so we can say that n c bar lambda by 3 dE by dx is equal to sigma T is equal to sigma T into dt by dx. Okay. So now we have to
Mom,
see.
there is negative here.
Yeah,
Mom,
there is negative sign, but अगर आप उसको नहीं भी लिखोगे, even then it will work, because negative sign simply means that your change of q or change of jq is in opposite direction to the change in the length. Okay, so that is just for a physical significance, in order to define the physical significance of this equation. अगर आप लिखोगे तब भी चलेगा, नहीं लिखोगे तब भी चलेगा. Okay,
okay, Mom.
so now let us consider this quantity n dE by dx is equal to, यहाँ से मैंने सिर्फ ये उठाया, dE by dx into n is equal to n dE by dt, ऐसे लिख सकते हैं इसको, into dt by dx. Okay, dt से मल्टीप्लाई किया, dt से डिवाइड भी किया. So this is further equal to, what is dE by dt? dE by dt is the specific heat of the solids. Okay, so dE by dt is, this is further equal to n into specific heat of the electrons into dt by dx. Okay, अब मैं क्या करूँगी इसको, this one n dE by dx I will be substituting from here to this equation number 3 में इसको substitute कर देते हैं. So this will become n c bar lambda divided by 3 specific heat of the electrons dt by dx. Okay, which is further equal to, मैंने कुछ नहीं किया है, सिर्फ उसकी वैल्यू सब्सटीट्यूट करी जो मैंने, जिसको मैंने ब्रेक किया था. ओके, which is further equal to sigma t dt by dx. Now let us compare on both sides, और लेफ्ट हैंड साइड को राइट हैंड साइड से कंपेयर करेंगे, so that sigma t is equal to this one, because dt by dx both sides it's equal. So sigma t is equal to n c bar lambda divided by 3 into specific heat of electrons. Okay, so let's say this is equation number maybe 3. Okay,
Mom, excuse me. What is
Yes.
that in subscript of CV, Mom?
yes, the CV is specific heat of the electrons. CV,
Mom, what is that subscript? D or theta?
no, it's C and subscript V.
Okay, that is electron. Okay.
Yes, this is electron. Okay,
Okay.
this is equal to specific heat of the electrons. Specific heat of the electrons. So this is specific heat of the electrons. Okay, so this is the situation when we are taking the classical conditions. Classical condition means, see, हमने यहाँ पे क्या किया, हमने mean velocity को consider किया है. C bar was the mean velocity of electrons. Mean velocity of the electrons. It means that we are, see, हमने क्या किया इसमें, this was the situation where heat flow was taking place, right? Here the electrons are being accelerated because of the temperature increase, right? And we are supposing that all the electrons are moving in this direction. Okay, but if you see the actual scenario, the movement of the electrons is very random. Okay, the electron may go here, the electron may go here, it may go here, it may go here, it may go like this or like this or like this. Okay, so the movement of the electrons is very random, right? Only a fraction of electrons are moving along this, right? Only some of the electrons are moving along this. Okay, but this has not been considered while deriving the equation number 3. We considered the mean velocity of all the electrons and then we took this model. But this is not the actual scenario. We have to take only those electrons which are actually moving from left to right. Right? So how to do that? See, it may be noted that heat current is generated almost entirely by those electrons which are close to the Fermi level. And if the electrons are below the Fermi level, they will cancel the impact of each other, right? If the electrons who are close to this Fermi level EF, right? If the electrons are close or this present at the Fermi level, they will be contributing for the heat generation. However, those electrons which are below Fermi level, they will cancel the impact of each other. They will not impact at all. They will not, generate the heat conduction. Okay, so this impact or this scenario we need to consider, and then we need to find out what is the actual thermal conductivity of the electrons. Okay, so if we consider those electrons who are present at Fermi level, then accordingly this equation will change. This equation is going to change. Okay, so let us consider the impact of those electrons who are present at close to Fermi level, right? So under that situation, the energy or the velocity of those electrons who are close to Fermi level or at Fermi level is given by 1/2 mvf square. This is the kinetic energy of the electrons. 1/2 mv square होता है तो Fermi level पे होगा तो vf हो जाएगा, right? So let us say this is equation number 4. And in equation number 3, आप लोगों ने फ्री इलेक्ट्रॉन थ्योरी पढ़ा है, आपने बैंड थ्योरी ऑफ सॉलिड्स भी पढ़ा है. So you must be knowing that the specific heat of the electrons at Fermi level is given by, ये आपने पहले आप derive कर चुके हो CMP1 में, so I'm not going to derive it again. So the specific heat of the electrons at Fermi level is given by pi square by 2 kBT divided by EF. EF is the Fermi energy, Kb is the Boltzmann constant, T is the temperature, N Kb, N is the number of electrons. Okay. So if we put this value of Cv from equation number 5 in equation number 3, the equation number 3 will be modified to one second please. Yes. So if we substitute equation number 5, the value of CV electronic heat of the specific heat of the electrons from equation number 5 to equation number 3, the thermal conductivity of electrons, equation number 3 will be modified to sigma T is equal to 1 by 3 uh, CV की वैल्यू क्या है पाई स्क्वायर बाई 2 के बी टी बाई ई एफ के बी एन. And now see, one thing we have to do, since we are talking at Fermi level, so what is C? C was the mean velocity of all the electrons, but we are talking about only those electrons who are present in the Fermi level, and the velocity of those electrons is Vf. Now instead of C bar, we will be writing it as Vf. Okay. Similarly, mean this is the lambda is the mean free path. So mean free path at Fermi level, we will say this is lambda f. So C bar will be replaced by Vf and lambda will be replaced by lambda f. Okay. So this equation will become Vf lambda f, and it could be simplified further. So this is equal to pi square by 6 n kb square t lambda f Vf divided by Ef. Okay, so again one modification could be done over here, because we know that at Fermi level the velocity of the electrons is given by Ef is equal to 1 by 2 m Vf square. तो यहाँ से Vf की वैल्यू आप यहाँ पे सब्सटीट्यूट कर सकते हो. So this could be written as pi square by 6 into n k b square t lambda f Vf and sorry yeah, so Vf would be just a minute.
Ma'am, 2EF upon M under the root.
Yeah, just give me one moment please. Okay, so this is 2EF divided by M, and here we have EF also. Okay, and one thing more, what we are going to do is we are multiplying this by Vf and dividing by Vf also. Okay, so this will be okay. Just do one thing. EF की वैल्यू यहाँ पे सब्सटीट्यूट कर देते हैं. So EF is 1 by 2 mv square. Okay, so this will be m, yeah, 2 divided by m Vf square. E की वैल्यू को आपने सब्सटीट्यूट कर दिया सिंपली यहाँ पे. So this is like this. Just a minute. So this will become, we are substituting the value of EF from here. This is 1 by 2 mVF square. So this will become 2 divided by mVF square. Okay. So this is further equal to sigma t. Let us simplify it more. This is equal to 2 है, यहाँ पे 3 हो जाएगा. So this is pi square by 3 and n kb square t n kb square t divided by m and lambda f upon vf को हम लोग बाहर ले लेंगे. ठीक है. So this is lambda f by, yeah. So this is known as, what is lambda f by vf? Lambda f by vf is known as the relaxation time of the electrons at Fermi level. Okay. So sigma t is further equal to pi square by 3 n kb square t upon m into tau f, where tau f is equal to lambda f upon vf. Okay. So sigma t is equal to this one. Okay. So this is the expression for the thermal conductivity of metals. This is the expression for the thermal conductivity of metals. Thermal conductivity of metals. This is very important article. Most of the times it has been asked in exams. So this is important for you. Okay, one thing more. See, this is the thermal conductivity of the metals, and we also know what is the expression for the electrical conductivity of the metals. Electrical conductivity of the metals is given by Ne square tau f Ne square tau f divided by m. This is the electrical conductivity. This is the electrical conductivity. Okay. So if we take the ratio of thermal conductivity and electrical conductivity, then sigma t by sigma will be equal to pi square by 3 into n k p square tau f t divided by m this is what? This is sigma t, और divided by sigma करोगे तो sigma आपका ऊपर आ जाएगा what? m divided by n e square tau f. Okay. So इसको simplify करोगे, you will get this is equal to pi square by 3 k t upon electronic charge e square multiplied by T temperature. Okay. So this is the ratio of the thermal conductivity to electrical conductivity. जब आपने free electron theory पढ़ा था, you might have studied what is Wiedemann-French law. Wiedemann-French law is the ratio of thermal conductivity. Wiedemann-French law states that the ratio of the thermal to electrical conductivity is directly proportional to temperature, right? So we have proved that the ratio of thermal to electrical conductivity is proportional to temperature, means sigma t on sigma is proportional to is proportional to temperature. Is proportional to temperature. And moreover, there is one more quantity which we define for metals, and that is Lorentz number. By using this ratio, Lorentz number L is defined as the ratio of thermal conductivity to the product of the electrical conductivity and temperature. This is known as the Lorentz number, and this is equal to, from this equation if you see, this is equal to what? This is equal to pi square by 3 pi square by 3 into kb अपॉन E. ठीक है, T को हम उस तरफ ले गए हैं. So this is known as the Lorentz number and its value is equal to 2.45 into 10 raised to power minus 8 watt ohm per Kelvin square. Okay, so this number, this Lorentz number is a constant and it is same for all the metals. This also suggests that the electrical and thermal conductivities of metals are closely related, right? Why this is related? See, this is a very much expected thing. Why? Because in both cases the charge carriers are electrons. थर्मल कंडक्टिविटी भी इलेक्ट्रॉन्स की वजह से है, इलेक्ट्रॉनिक कंडक्टिविटी भी इलेक्ट्रॉन्स की वजह से है. So because in both of the cases the carriers are electrons, so there must be some relation between the thermal conductivity and the electrical conductivity, right? Okay, so this is all about the thermal conductivity of the metals. And you want to ask something? Yes.
Yes, ma'am.
Yes.
This is KB E whole square, right?
Yeah. Kb divided by E. Kb is the Boltzmann constant. E is the electronic charge. It's whole square.
Okay, ma'am.
Yes, students. Anything that you want to ask? Any questions, students?
No, ma'am.
Okay. So that's all for today. Another article. So there are, I think, 2 articles are left. On Monday, most probably will be completing this chapter. Okay.
Okay, ma'am.
Yeah. Thank you, students. Have a good day.